Today's webinar, titled 3D Printing, Turning Ideas into Reality, is presented by Dr. Denis Cormier, the Earl W. Brinkman Professor of Industrial and Systems Engineering at RIT. Denis also serves as Director of the Print Center that conducts applied 3D printing and additive manufacturing research. He has worked in 3D print and additive manufacturing for 20 years with a specific focus on aerospace materials and applications of metal additive manufacturing. Most recently, his research has focused on developing next-generation 3D printing technologies capable of printing parts with multiple materials. Denis is a founding member of ASTM's F42 Additive Manufacturing Standards Group, and he is a longtime organizing committee member for SME's Rapid Conference and Exhibition. He serves on the editorial advisory boards for several journals, including the Rapid Prototyping Journal, the International Journal of Rapid Manufacturing, and Additive Manufacturing. We are very, very fortunate to have Dr. Cormier with us for today's webinar. Welcome, Denis, and now let's get started.
Okay, thank you, Cindy. And let me make sure, are we in full screen mode here? There we go.
Yes, we are.
Okay, well, we'll go ahead and get off. I will give a quick disclaimer that while Cindy was giving her her introduction, a notification from Microsoft popped up that it was downloading and installing software. So I'm crossing my fingers that this goes without interruption here, but we'll roll with the punches if Microsoft chimes in. So, as Cindy said, I'll give a talk about 3D printing here, and I'm happy to answer questions. I'll take a break in the middle if there are intermediate questions, and then we'll address more questions at the very end. So, quick overview. Most people are familiar with 3D printing processes up to this point in time. I'll give a quick overview just in case anybody's new to it. But I'll spend some time talking about different ways to do 3D printing, which is also known as additive manufacturing. Most people are familiar with the MakerBot style extruding plastic through a moving nozzle, but there are a lot of other ways to do 3D printing, including with metals. So I'll talk a little bit about those, and then I'll close with a description of some of the more interesting 3D printing activities that are currently taking place at RIT. So the basics, most 3D printing or additive manufacturing processes involve printing or depositing one layer of material on top of the next. And in the same way that there are a lot of ways to print documents or photographs, there are also a lot of ways to 3D print materials. But the primary distinction here is that when you apply one layer on top of the next, you build thickness, and that thickness is the third dimension in 3D printing. So there's a list of different processes there. I'll talk about some of them in the following slides here. So the first thing before we talk about this process is why are we even talking about 3D printing at all? What's the big deal? And a big part of the big deal there is the impossible geometries that you can 3D print shapes that are impossible to mold or cast or machine, such as the ones you see right there. So the image in the upper right-hand corner there, that's an example, it's a computer design of a hip stem. If somebody has arthritis in their knees or their hips, you have a titanium implant put in there. And what you're seeing there is a design that a former student of mine did for a titanium hip stem where the 3D printed titanium stem would have the same stiffness as the human bone that it goes into. And the idea there is that by matching the stiffness to the bone, of the implant to the bone that is, the implant itself is not taking all of the load when you're walking. And because if that happens, then you start to lose bone mass around the implant, and that's when the implant loosens and you have to have a revision surgery. That's a great example of a geometry that you can 3D print in metal, in this case, absolutely impossible to machine or cast something that intricate and that complex. The other thing, I won't touch a whole lot about it on this in the presentation, but it's quite relevant to the whole Rochester region, is printing with multiple materials. So in the same way that Kodak or Xerox or any other printing company can print multiple colors like cyan, yellow, and magenta, in a 3D printer, you can print different types of materials instead of colors. And I'll give some examples of that in a little bit. But that multi-material 3D printing, in my opinion, is going to be the next big thing in 3D printing. 3D printing can't do everything. There are limitations, and it's important to recognize them. 3D printers are very, very slow compared with conventional manufacturing, molding or casting. What you save in terms of time is the time it takes to make molds that you would cast plastic or metal into. So you do save time on making molds, but the printing process itself, a lot of these are a little bit like watching grass grow, except that grass grows faster in some cases than some of these 3D printers. Most 3D printers are limited to relatively small, let's say 8 to 10 inch cube part sizes. So, that's fine for a lot of parts, but if you're in the aerospace or automotive industries, that's quite limiting. The cost of the equipment, maker bots are on the order of $2,000 now. The machine that you see on the right-hand side of that image right there is almost $1 million, and that's for making metal parts. That was a machine in my old lab before I joined RIT. And the consumable materials that you print with these machines are also quite expensive. So in a lot of cases, they might be 5 to 10 times more expensive than the same material that you would mold or cast. So that's a challenge that I think the industry has to try to overcome in the coming years before these technologies gain more widespread adoption. So let's talk about some different ways to 3D print parts now. What you see in this image is one of the few processes we don't have here at RIT, but it's worth pointing out simply because there are two very well-known document printing companies here in Rochester. So this is a paper printing process by MCOR in Ireland. It uses ordinary office paper as the feedstock material, and you inkjet print a color image onto the sheet of paper, and a knife cutter cuts the contour around the color printed region. The machine applies an adhesive material. You lay down the next layer of paper, repeat the process over and over again, and when you're done, the knife cutter has cut cubes into the scrap material around your part, and you can just pick those cubes off with your hand or a screwdriver, something like that, and you have a color printed part made out of paper at extremely low cost. That's kind of a neat process that has a lot in common with some of the technologies that this region is very well known for. Plastics, the majority of 3D printers work with plastic materials. One of the best known processes is fused deposition modeling, or FDM. So the video that you hopefully see playing right there is a MakerBot that is laying down the plastic. MakerBot is headquartered in New York City. And if you're not familiar with this process, you just put plastic, looks like weed whacker wire, but plastic wire or filament into a heated nozzle that's a lot like a glue gun, hot melt glue gun, and that's moving around, so it lays down this bead of plastic one layer on top of the next. And the images that you see at the bottom there, that was a ukulele that some students taking the 3D printing class, the students who take that class always do a course project. So one year the students did a course project on the theme for the entire class was, for their projects, their design projects, the theme was musical instruments. So each group of 2 or 3 students had to design and 3D print a musical instrument. This was one example where they were able to pause the 3D printer at different points in time in order to change the color of the plastic and do an RIT-themed ukulele. To the best of my knowledge, Bill Dessler has not played this ukulele, but he does know it exists, so maybe we'll get him to play a song on it someday. Selective laser sintering is a higher-end 3D printing process in which you have plastic powder, a thermoplastic powder, and a doctor blade just spreads a thin layer of that plastic powder, and a laser coming from overhead scans or traces the contour and then rasters back and forth and fills in the region that you would like to melt. So anywhere the laser beam scans over the powder bed, it melts the plastic, and it does it in the same way that you might, if you were drawing with a crayon, drawing an image with a crayon, you trace the contour and then scribble back and forth to color in the area inside the contour. In this case, it's a laser beam that's melting a thin layer of plastic powder. Then the doctor blade spreads another thin layer of powder on top of that first layer, and the laser melts the second layer, and then you do the third and the fourth and so on, and you get a part that looks like what you see in the image right there. And if I play that again, one of the interesting things in this particular video that I shot with my cell phone, that comes out of the machine exactly like you see right there. So that's an assembly where the small gap in between the moving gears and the pins in the middle of the gear is filled with unmelted, just a few particles of unmelted plastic powder. So when you're done printing, you just wiggle those moving parts back and forth, and the loose powder falls out. So that's kind of an interesting aspect of 3D printing, is the ability to make moving assemblies of parts without having to do assembly after the fact. Stereolithography, like you see in this video right here, that was actually the very first 3D printing, commercialized 3D printing process. So in the vat, in that tank that you see right there, there is a vat of a liquid plastic, and it's called a photopolymer. So anywhere that blue laser beam scans over the vat of plastic, there's a chemical reaction that causes only that plastic to harden. It goes from a liquid to a solid, and then you have a doctor blade there that spreads a thin layer of plastic, liquid plastic, on top of the previous layer, and you repeat the process, and now through the magic of Adobe Premiere, you fast forward to the end. So this machine was in my old lab at NC State. We have newer versions of this process right now, but that's a 3D printed skull model right there with a really nasty skull fracture right there. Okay, so this is what's called stereolithography. And one of the newest types of 3D printing is a projected image 3D printing. And this is a fast motion video. Students at RIT built this. Now you see it in real time. There's a vat of liquid right there, liquid plastic. That bright light that you're seeing there underneath this machine is an ordinary overhead projector like you might have in a classroom. And that projector projects a black and white image up through the bottom of the tank right there, which is clear. So anywhere that projected image is white, it causes the plastic to get hard. Anywhere the image is black, the plastic just remains liquid. And in this case, we're actually building the part upside down. So the part itself sticks to this build platform. The abominable snowman that you see right here was the very first successful build that the students did using this machine that they had constructed. And it's worth noting that they made their own plastic resin used in this machine as well. They didn't purchase the resin. They mixed it up themselves. So this was a nice learning exercise for the students. And machines like this are commercially available for on the order of $3,000, give or take, right now. Changing gears, you can have binder jetting processes the video that you see right there, that's plaster powder like we might have used when we were kids in art class for plaster of Paris. When you mix water with plaster, the plaster gets hard, once it dries, of course. In this case, the carriage that you see going back and forth right there is a Hewlett-Packard color inkjet print engine, and the liquid droplets in the colored ink right there, the liquid in the droplets reacts with the plaster powder, and the plaster gets hard only where you've jetted the colored ink. And anywhere outside of that colored ink, you just have loose plaster. So you finish, you print one layer on top of the next, let it dry, and dig your hands in there, pull the parts out, and blow it off with compressed air, and you end up with something like you see in the top there. Those were the Tiger dice. I designed those maybe 3 or 4 years ago for the Imagine RIT Festival as a handout. So we had this machine running at the Imagine RIT Festival, printing these Tiger dice, Tiger-themed dice, and then I handed them out to the attendees, and the students handed them out and kept the machine running. So it's a pretty fast process, and the consumables are relatively inexpensive. The parts themselves are plaster, so they're not terribly strong, but it's a great visualization tool for color 3D printing. We get to inkjet based, and this is where a lot of the, I guess I would say, cutting edge or next generation 3D printing developments are taking place. So Stratasys and 3D Systems are the two primary companies working with this particular process. So the idea here is that it's a color inkjet print engine like you normally would use with colored ink. The difference being that the ink that's being printed, inkjet printed, is actually a liquid plastic, the same type of plastic that you saw a couple slides ago with stereolithography and with the projection-based machine. So you're able to inkjet print. I'll go ahead and run this one more time. You can inkjet print color liquid plastic. And you'll notice when the video is running, there's kind of a bright light, that blue flash that you see right there. That's an ultraviolet light that anytime you shine that light on the plastic gets hard. It turns from a liquid to a solid. And so that's how you can print color plastic, functioning plastic parts in 3 dimensions by printing one layer on top of the next. And this right here, this is a machine that we just got we just got delivered to the lab about a couple weeks ago. The installation and training for this is going to take place next week, but we have one of these 3D printers in the lab now. And this is the upper right corner there. That anatomical model is an extreme example of what's possible with inkjet-based 3D printing, where you can print full color, including clear materials, and even blending flexible plastics and rigid plastics all within the same part without any assembly. So this is really exciting, and I think there are tremendous advances that are yet to come with this type of technology. So can metal parts be 3D printed? And the answer is absolutely. So here's an example of an electron beam melting process. The same thing can be done with laser beams. And you spread, in this case, I'll run this video a second time here. Inside the machine, you spread a layer of titanium powder or whatever metal powder you're interested in, and then an electron beam or a laser beam scans anywhere you want to melt the titanium powder. So that's what you saw in the video there. The reason it's a little bit tough to see what's going on here, the titanium melts at well over 3,000 degrees Fahrenheit or over 1,500 degrees C. And so you have to have a pretty bulky machine to protect the environment from those high temperatures. And in this particular video, the video is shot through a leaded glass window. So it's a little bit tough to see what's going on in there, but you get the idea. and you can spread a second layer of metal powder on top of the first and repeat the process and get, you know, odd shapes like you see right here. So this was a titanium part that I did for a NASCAR team a number of years ago. That's not the whole part. I can't show the whole part, but that's a portion of a build. Okay. So binder jetting is possible with metals as well. So I showed the plaster process a couple slides ago. This is the same. You can do the same process using metal powder instead of plaster powder. The only difference is the ink that you're jetting onto the powder bed has a little bit of a polymer glue in it, and that polymer glue holds the metal particles together anywhere you jet it. When you're done, you take that part, put it in a furnace, and the metal particles fuse together, and the plastic glue that's holding it together just burns away, and you're left with a part like you see right here in this image. So this was the College of Engineering had a leadership medal that was awarded last year, and they asked me to design something that could only be done with 3D printing, and it's named after Kate Gleason. So I laser scanned the bronze bust of Kate Gleason in the hallway upstairs, and that's the scan, a miniature scan that you see. And then I designed the lattice structure and everything else around that. And this was printed in a bronze steel material that you see right here. So nice example there of how that works. So why don't I take a break right here to answer, there have been 4 or 5 questions that have come in, and if I'm on full screen, I can't see the questions. So Cindy, maybe if you'd like to read out the questions and I could respond, would you like to do it that way?
Yes, several have come in, and if we go back a bit, some were specific to some of the processes you were describing.
Okay.
So one of the more general questions has come in from Kevin, and it's specific to why is the process so slow?
So if you compare it with injection molding or casting metal, you have a mold, you have a machine cavity in a steel mold, and you melt plastic and you just inject it under high speed and it fills up the entire mold all at once. With printing, think back to like the MakerBot process where you melt, or actually the best example I can do is if you're using a magic marker and you wanted to draw a complex picture, I don't know, a rainbow, let's say, you would draw the rainbow, the outline with the crayon or a magic marker, and then you'd pick up whatever color you want and you color back and forth. So the amount of time it takes for you to draw that one layer is a function of how much material or how much area there is to print in that layer. And if you do that that's one layer, and in 3D printing you have to do thousands of layers. So it's a single nozzle moving around, and that just takes a really long time, like you saw in some of those videos. Inkjet printing is inherently faster because you have a line of inkjets all printing at the same time, but you do still have to sweep that head back and forth a number of times. So there are people that are working on speeding up 3D printing. Frankly, if you go look at Kodak and Xerox, the very high-end print engines that they have, where they can print hundreds of layers, or sorry, more than 100 sheets of paper per minute on their very high-end print engines, it is possible to print a lot of layers per minute if you were to translate their technologies into the 3D printing world. But most of the printing companies, document printing companies, have not yet made the leap into 3D printing. That is starting to change, though. Hewlett-Packard is investing massive sums of money getting into the 3D printing market, and I hope that most of the other big printing companies will follow suit. And you will see faster 3D printing processes when that happens.
Question from Gemma. The question is specific to, is 3D printing going to become a financially preferable option to manufacturing?
So I don't see 3D printing ever taking the place of high volume injection molding or metal casting processes for the reasons we just discussed. However, as the processes get faster, it will become economically preferable for all those cases where you only need to make, you know, one of something, or tens or hundreds or single digit thousands of something. In those cases, the answer is yes. And the reason for that, if you're injection molding or casting something, you're spending usually at least $10,000 for a really simple mold, up to hundreds of thousands of dollars for an extremely large complex mold. And the cost of that mold has to get absorbed by the number of parts you make. So it's only economically preferable to injection mold or cast very large quantities of parts. Otherwise, you just can't amortize the cost of the mold. So that's where, as 3D printing processes get faster and faster, the economic crossover point gets, will start to get into the thousands of parts instead of today it might be hundreds of parts.
How about just one more question? There's a lot of them in here, but I know you have more presentation. There's
Sure.
One question specific to, is there a standard or accepted process for quantifying and qualifying the strength of 3D printed products? That question comes from Michael.
Yes, good question. And there, ASTM has the F42 Standards Committee, which I'm part of that. And the F42 Standards Committee develops testing standards specifically to assess what you asked about. And it's a good question, because anytime you build parts in layers, it's a laminate, right? It's a lamination. And in the same way, if you bend a sheet of plywood, the plies of the plywood will splinter and delaminate. For some of, particularly the plastic 3D printing processes, that you can get that same delamination, or it's weaker in the vertical direction that you're building the part. So yes, there are testing standards. For metals, that lamination effect that you see in metals is actually not as pronounced. So metal additive manufacturing is being used in the aerospace industry right now to make some production parts. But medical and aerospace qualification is an extremely expensive process, so it's taking a little bit of time to roll out. But there are some good success stories out there right now with GE and others.
Thank you. Do you want to continue, or do you want me to give you some more questions? Up to you, Dennis.
Why don't we take two, I'm looking at the clock here, why don't we take two more questions, and then with whatever time is left at the end, we'll try our best to answer the rest of them.
Okay, how about a question from Jesse? What are the biggest challenges of 3D print to entering the consumer market, like with personal computers?
So the cost and speed, frankly, are the biggest ones. So the cost of the hardware is starting to come down. There are some more affordable 3D printing platforms that produce very high quality parts. And I'm more talking about plastic parts initially. However, the consumable, the plastic that you put in those 3D printers, is still quite expensive compared with the same plastic that you would injection mold plastic parts, consumer plastic parts out of. And so an example of that, for the liquid plastic processes that I talked about, like stereolithography, those materials can cost at least $500 to as much as $1,000 per gallon of plastic for that those liquid resins. And that's really expensive when you compare you compare it with the cost of 50-pound bags of plastic, or bins of plastic that are normally used in an injection molding machine, that are a fraction of that price. So the cost of the consumables really is a barrier, and it's going in the right direction, but there's still a fair amount of work to be done. I think when we start to, where things get really interesting on the consumer side, specifically for this question, is when you get into the color 3D printing, like that Stratasys anatomical model that I showed. If you're a marketing person at a company and you say, I can injection mold a plastic part in, this palette of individual colors, and I could put decals or something like that on there if I want decoration. But with a color 3D printer, if I say for small quantities of parts, we can 3D print this plastic part with any color, multicolor scheme you want on it, with logos and all sorts of things, and three-dimensional surface texturing and whatnot. There's some really exciting opportunities out there for graphic designers and industrial designers and those types of folks for consumer products that are manufactured with these full color types of processes.
Thanks, Dennis. One quick two-parter question from Chris. Which startups are most compelling in this sector, and how are the incumbents like Hewlett-Packard reacting to this disruptive technology?
Well, that's a tough question to answer in the first part of it, what startups are compelling, because almost on a daily basis there are 2 or 3 startups that claim they're going to change the world of 3D printing. One that's gotten a lot of press recently is Carbon. They were called Carbon 3D. Now they changed their name to Carbon. And Kodak, just as a regional point of interest, Kodak recently, maybe 2 or 3 months ago, announced a partnering deal with Carbon, where Kodak is working on photopolymer development, or the liquid plastic, the consumable materials for Carbon. So there actually is a Rochester connection with that startup. But that startup was born out of the University of North Carolina at Chapel Hill. Joe DeSimone was a professor there and a joint appointment at NC State. They moved the company to California because they had Silicon Valley connections there. It's my understanding that Carbon got something like $150 million in venture capital funding, that's a lot of money for a startup, but their process is very fast, produces the highest quality 3D printed plastic parts that I have seen at fairly high speeds. So that's a particularly compelling one. Aside from that, it's some of the bigger companies. That's the startup that I would point to initially. How is Hewlett-Packard, the second part of your question, how is Hewlett-Packard responding? The Hewlett-Packard and all of the other large printing OEMs have been reluctant up to this point, because as big as the rest of us think the 3D printing market is, it's still relatively small by document printing standards. However, it's growing. The compound annual growth rate for the 3D printing industry worldwide is over 30% per year for the last 5 or 6 years. So there aren't too many industries that are growing at that clip. And, so I think it's one of those things. It will get there, and it's, how quickly the companies pull the trigger, the HPs and other printing companies. I hope our local companies don't sit on the sidelines too long, until it's too late for them to make a big splash in here. But every large OEM, HP and others, has either just gotten into the 3D printing industry or is looking very closely at it and doing some preliminary R&D. Okay.
Thank you, Dennis. We do have other questions, but we will try to get to as many as we can toward the end of Dennis's presentation, and I promise that those questions we do not get to, we will get answers and email them to all participants. Sound good, Dennis?
That sounds good.
Great. Take
all
it
right.
away.
Yep, we'll transition. So I've talked about what some of the different ways to 3D print are. And now I'll transition to some of the specific things that are taking place at RIT. About 3 years ago, President Dessler wanted to create a space where students anywhere on campus, completely independent of academic program or college or anything like that, any student anywhere on campus had a home where they could come and turn their ideas into reality. So this is a snapshot of the student maker space, which they call the construct. And on the left-hand side of that image against the wall, you've got the 3D printing space. All the way on the right-hand side there's electronics, soldering, and so on. In the back there, you have a CNC router, there's bandsaws, milling machine, et cetera, et cetera. This is a really, really nice space. And like I said, this is not owned by any college. This is open to any student on a walk-in basis. They just have to tell the lab manager what it is they want to do, and as long as it's reasonable and safe and so on, then they have free reign of the space there. The Imagine RIT Festival is actually one of the biggest consumers of 3D printing capabilities on RIT's campus. So you're all the attendees on this conference call are RIT alums, and so you're presumably familiar with the Imagine RIT Festival. If you're from out of town and haven't attended it, I highly encourage you to do this, because there are over 30,000 attendees every year for this one-day festival. And it's an event where students, it's primarily student-driven. Students from all over campus spend a lot of time during the academic year leading up to May coming up with cool and fun ideas of things that they would like to display or exhibit at the Imagine RIT Festival. And a whole bunch of those ideas get 3D printed. And what you see in this image right here, this is a chemical engineering student named Yasha, who has working on the Enable project, which I'll actually mention in a few slides there, for 3D printing of prosthetic hands. But a lot of the other, lots and lots of Imagine RIT exhibits are made possible because of 3D printing capabilities on campus. This was an interesting one. A biomedical engineering student named Kayla Wheeler, who you see right there. She played soccer and basketball, both of which are sports where the athletes can get concussions heading a soccer ball, or collisions between athletes on the basketball court. So she had an idea for this protective headband that you would wrap around your, but you're all familiar with headbands, right? But the headband would have 3D printed rubber cushioning sewn into this band. So she and another student co-founded this startup company, Volatile Padding Technologies. To be honest with you, I don't know where things stand with the startup right now, but the idea was to try to make these available to athletes to try to reduce the incidence of concussions. And what you see in this little video right here that I'll play in a second, there are examples of rubber, 3D printed rubber material where in one side I put a special type of fluid in one, and it's not in the other, and when the steel balls bounce, you can see one of them on the left does a much better job of absorbing the energy than the one on the right there. So this is an interesting use of 3D printing that was student-driven, again, with a very specific need. The Enable project that I mentioned a little while ago, there's John Shull is an employee here at RIT who leads up this Enabling the Future website that you see, and this is for 3D printed prosthetics, like you see on this young lady here with a 3D printed prosthetic hand. And there's a mechanism, and by flexing her elbow just a tiny bit, the linkages cause the fingers to grip. So that allows her, in this case, to ride a bicycle, which she couldn't previously do easily. There obviously are prosthetics, professionally made prosthetics that are suitable for adults. When a prosthetic is $50,000 or more and a child is growing every year, and anybody who's a parent on the phone call knows how often you're buying new shoes and clothes and things like that. So it's a difficult proposition to keep making new prosthetics every year or so while the child is growing. So that's one of the motivations here, but also in developing nations where it's just never, even for adults, it's not cost effective or feasible to have these very expensive prosthetics. So this is a great effort. The designs for different prosthetic hands and arms are open source and available. You can download them from that website, and anybody on the planet who has a 3D printer can download the plans, customize them, 3D print them for somebody who lives nearby. So that's another nice campus initiative. Here are a couple examples of 3D printing with medical instruments. So this was a project that I was involved with involving minimally invasive surgery for mitral valve repair in the heart. If you have a leaking mitral valve in the heart, they ordinarily would do open heart surgery where they have to cut your chest open. That's not minimally invasive, that's maximally invasive surgery. With minimally invasive surgery, they just make tiny incisions between the ribs, the cartilage between your ribs, and they can insert tubes that the medical instruments are inserted through those tubes. This specific project that was funded by the National Institutes of Health had us designing an automated knot tying mechanism, and that you see that prototyped right here. And this is another example of a prototyped assembly in which it was printed exactly like you see it right there. It comes out of the machine as a moving assembly, no assembly required afterwards. And so this was a nice use of 3D printing. There is a lot of call for medical models that you see. So using 3D printing to produce medical models that surgeons can use for pre-surgical planning, things like that. So this, the knee model that you see on the right-hand side there, Qmetrics is a local company here in Rochester that does medical imaging, and their software will take CT or MRI scans from the hospital and map the density of the bone to a color. So, red might mean low density bone or arthritis, soft bone tissue, and blue might be very hard, dense bone, everything's good, sort of a situation. This is an example of a medical model. In the 3D printing class that I teach, there were students that were interested in biomedical applications of 3D printing. So I gave them the model of the skull with a nasty skull fracture, and they had to design a custom bone plate that would be 3D printed in titanium, and the surgeon would then put it in place right there. So those are some examples of how here on RIT we're using these for medical models. This was an older case, but it's a nice one that I did back around 2003 or so. A German Shepherd with severely deformed hindquarters there. There's a special surgery. It's gruesome. It sounds gruesome, but they do this with people too. If the bone is curved, you make a cut in the bone, straighten the bone out, allow it to heal, and then everything's fine. This one was much more complicated because the bone was curved and twisted in multiple directions, so it was a really complicated surgery. The surgeon, Dr. Marcellin Little, who you see in the middle picture right there, he asked us to 3D print 3 sets of plastic bone models, which you see right there. He made he practiced the surgical procedure on the 3D printed models, and when he convinced himself that it was actually feasible to do the surgery, he called up the owner, and Bailey came in. Those are the lower left image there, shows 3D printed plastic models in the operating room where Dr. Marcellin would go over during the surgery and take measurements where he had made cuts to the bone and what angles and things like that, and then he would go back to Bailey, the dog, and replicate that. And so in the end, there's a very, very happy ending. Bailey went from not being able to walk to chasing the cat around the backyard. So we did a whole bunch of these types of pre-surgical planning for difficult procedures over the years. And this is a current ongoing project that multidisciplinary between David Borkholder, who's a professor of microsystems engineering here. He's the lead on this project, and we have several students from at least 3 different departments, 3 different disciplines working on the project. But this is a project to design, prototype, and test an implantable micropump for delivering drugs to the inner ear to treat hearing loss. And this is an example of next generation 3D printing where we are printing electronic materials, so we can print conductive silver or copper electronic traces, circuit board materials. We can print wax material that when wax melts, it expands. So we have this wax material that will expand, and when it expands, it squeezes the rubber tubing that has the drug in it, and when it squeezes the tubing, it pushes the drug forward. So that's how it's actually pumping, is by melting or solidifying wax. We have printed heaters and so on. So this is a really nice example of using multi-material 3D printing. There is no single machine capable of doing everything you see on that slide all at once. So we're actually using quite a few different steps, printing steps, to produce the prototypes of these devices. But the next generation 3D printing technologies will be able to do all of this all on one machine. Very exciting. So big picture, I think there was a question early on, some of the significance of 3D printing, and I did talk about impossible geometries and not having to make molds and things like that. But I'll also highlight what's on this slide, that prior to the advent of 3D printing, if you were a company that had very deep pockets, you have an idea for a new product, that's fine. You've got the budget, there was a model shop, you could make prototypes and evaluate them, and that was fine. But if you were an ordinary person who had a really good idea, which happens a lot, right, it was very often not practical or possible for those people to have prototypes made. With 3D printing now, there are maker spaces in just about every community, Rochester included, where anybody with an idea can go down to a community maker space and have a functioning model of their part 3D printed. There are lots of local service bureaus who 3D print professionally and do a fantastic job of it. And even kids in elementary schools, middle schools, and high schools have 3D printers in their libraries or their first robotics teams or things like that. So I think this is one of the biggest impacts of 3D printing. Is it's really accelerated the rate of innovation and who has access to be able to turn their ideas into models and hopefully into startup companies or licensed technologies, things like that. This was an example that I was approached a number of years ago by a school teacher who had an idea. She said, every day practically we have to staple pieces of paper or cardboard or whatever to the cork boards in classrooms or in the hallways. And she said it's really hard if you're trying to hold a piece of paper with one hand and operate the stapler with the other hand. So what she wanted to do was have one of these, a one-handed stapler with a strap like you see in the lower image there. So take those two pictures and merge them together. And so I helped her with the 3D printing of her idea. She was able to take that to a business competition, a Staples business competition, She didn't win it, but she did get a runner-up award, and I don't know if it's still available, but it was my understanding that Staples was selling these at least once upon a time in their website. So that's a nice example of a school teacher who had an idea, and 3D printing allowed her to take a functioning prototype and show it to somebody who helped her commercialize it. A current term example is this gentleman named Joe Cabes, who is a physical education instructor in Webster, and he works with a number of children with special needs who are in walkers and wheelchairs and things like that, and he wanted to come up with a way that would allow those kids to be able to participate in gym class, but really just allow them to play in ways that they hadn't been able to play before, instead of just watching the other kids play. So he designed these fantastic attachments that can clamp onto walkers and wheelchairs and things like that. So the lower image that you see there is a ramp that when you see the bowling pins on the right-hand side, so the child can line up their walker and let go of the ball and try to knock over the bowling pins. On the top image there, a soccer ball or a basketball, something like that, where the child can use their hand to raise or lower the hoop that you see right there. So Joe had this, he had this idea, and he had mocked up some prototypes himself, just using stuff he could get at Lowe's or Home Depot. But we've got a project, we're putting the project together this summer, and this will be a senior design project this coming year in engineering, where they will design more production-ready hardware for Joe, and then we'll use 3D printing to print prototypes of that hardware to make the examples that he can take. Sorry about that. That he can take to a production company to try to get these things made. So the web link on the bottom right there has some of the details and some of the other examples of prototypes that Joe has made. So I love that example as well of a person who has been able to turn his ideas into reality. So to close things up here, looking forward, RIT just a few months ago got funding from New York State for a new Center for Advanced Technology, or CAT, that is focused on additive manufacturing and 3D printing. So the lower image that you see right there is what the space looks like today. And in October, we will have our grand opening with all the new equipment that's going in there. Right now, we're cramming all the equipment into the lab that you see on the top there. But this will be a beautiful facility when it's ready in October. And with that, I have maybe 5-6 minutes for questions.
Yep,
I'll try to talk fast.
Yep, we've got a couple. We have several, but we can only get to a couple. So this question comes from Bruno. Has 3D printing been done with organic materials for things like skin grafts?
Yes, definitely. So there are, we're not doing it here at RIT, but there are folks at Wake Forest University and Harvard and some others that are, inkjet, for instance. If the liquid that you're inkjetting, instead of cyan, yellow, and magenta pigments, you might be inkjet printing stem cells. So yes, it is biological materials, things like that are definitely possible. And that's realistically a lot of that work of printing replacement organs is 20 or 30 years away to actual implementation with people. But there are some short-term, cartilage and skin and things like that are very short-term possibilities.
Great. Question from Henry, which is quite topical given what's been in the news in the last week and a week or so. Henry, although he is a supporter of the Second Amendment, he is concerned about people using 3D printing to make guns. What's happening in this area?
So there's a gentleman named Cody Wilson in Austin, Texas, who about 2 or 3 years ago posted plans on the internet for people who could 3D print their own guns. The federal government did not take a shining to that and ordered him and everybody else to remove the plans from the internet. That hasn't stopped everybody. My short answer to that, if somebody really wanted to make their own gun, going down to a Harbor Freight and buying a $3,000 milling machine, it'd be a much safer gun to fire than a 3D printed gun. So I would be nervous about putting one of those guns up next to my cheek, but people are doing it, and you know, instead of buyer beware, it's builder beware, I guess, is the caution right there.
Okay, thank you, Dennis. There is a question here from, and I got to scroll up. Janelle wants to know, how do you describe or tell the printer what it is you want it to print? Okay, good question. You obviously have to have a design. You're correct. You have to have a design. There are lots and lots of websites, Thingiverse and other places, GrabCAD, where you can download models from someone else. But if you want to make it yourself, you have to have a computer-aided design or CAD software package where you design the geometry that you would like to print. Regardless of which software package you use, you typically save it in the STL file format, and all 3D printers will then be able to print STL files. Fantastic. I am looking to see if you've got a number of great compliments, Dennis, so thank you. One last question. What are the limitations in size and resolution of a print, and which process has the highest resolution in metal or in plastic?
Oh boy, unfortunately, that's an almost impossible question to answer because there's such a huge range. The filament extrusion type processes generally have the poorest, or the largest features. The inkjet printing processes can get down to 14 or 15 micron layer thickness. And just to give you a frame of reference, the diameter of a hair on your head is roughly 60 microns in diameter. So you're about a quarter of the diameter of the hair on your head. That's a pretty small feature. So inkjet systems can get very fine features. And the build volume is all over the place. There are really tiny ones and really large ones, and that's just a function of how many zeros you have in your bank account. Whether or not you can afford the large systems. On the metal side of things, the laser-based metal additive systems have the parts will come out with a rough textured surface, kind of like a sand casting, but the laser-based systems generally have better feature size and resolution than the electron beam systems. The electron beam systems can do much larger parts faster than the laser-based metal systems. So the laser-based systems tend to be used for smaller parts with finer detail.
That's fantastic.
I could go on for an hour on that question, but I know we're out of time. So.
I know we are out of time. It is on the hour, so I would like to thank Dennis extremely much for being our presenter today. This was a very fascinating session. There are tons of more questions, and they're still coming in. Rest assured, we will capture all of those. We will get them over to Dennis and do our very best to get each and every one of you some answers. So that is all the time we have. Again, any more questions, you can email them to ritalum@rit.edu. Dennis also shared his direct email. Thanks again to all of you for joining. Our next webinar is on July 12th, where we talk about cloud-enabled by Craig Branditz, I'm not going to say it correctly, Branditz, who is an alum from the class of 1991. So thank you again for joining. Thank you, Dennis, for presenting.